Well, after some very interesting keynote speakers, it's time to take a more detailed look at flexibility in Great Britain and the report itself. For me, and I think the industry, previous modelling by the Carbon Trust and Imperial College has produced some important insights. So I, for one, am very interested to see the results of this new and much more comprehensive work. I'm clearly not alone in that, as well over 1,000 people have signed up to attend this week. I better not keep you from hearing the detail any longer. We're going to kick off with a couple of presentations on the report, then I have some questions about it, and I hope the audience will have questions as well. So first, I'd like to introduce Andrew Lever, a director at the Carbon Trust, and he is a champion of whole systems thinking and applies this to support new approaches and innovation in renewable system integration. Go ahead, Andy.
Thank you, Janet, and good morning, everyone, and good afternoon if you're joining us internationally. As Janet said, yeah, I've got the pleasure of presenting the key findings of the Flexibility in Great Britain project. I think we have some slides. So moving on to the first slide, this project, of course, very much set out to understand the role and value of flexibility in meeting net zero targets. This builds on our 2016 analysis on electricity flexibility for BEIS, which is still used today by the sector as a robust evidence base on the value of flexibility. And we've updated and expanded the analysis to cover heat, transport, hydrogen, and power in a net zero energy system. The report is the output of 18 months of rigorous independent analysis, and given the transition to net zero energy system will require significant collaboration, we convened a cross-sector consortium and worked again in partnership with Imperial College London. To support decision-making through the project, we engaged closely with BEIS, Ofgem, the Climate Change Committee, National Infrastructure Commission, National Grid, ESO, and Innovate UK to make the findings as relevant and robust as possible. Now, the report takes a scenario-based approach to lay out 3 different 2050 futures driven primarily by the heat decarbonisation strategy, be that electric heating, hydrogen heating, or a hybrid heating approach, which is heat pump with backup natural gas boilers. These were chosen as heat decarbonisation routes are subject to large uncertainty and also have a significant impact on the shape and form of the wider energy system. The modelling analysis highlights the role and value of flexibility alongside these heating approaches. This allows a greater understanding of the type of flexibility technologies required, including how they interact with the heating system to meet demand and with the wider system to reduce costs. Each scenario is analysed with and without additional flexible technology deployment to determine the impact of flexibility across key metrics such as system cost, system demand, electricity generation capacity, and emissions profiles. In addition, the report undertakes a range of sensitivity analyses across 3 scenarios to understand the impact on the wider system of key uncertainties in a 2050 energy system. You can see these across the bottom of this chart, and they include a diversified and dominant hydrogen production pathway, the impact of carbon negative technology availability, the cost and availability of key flexible technologies, the optimization of system costs for local or national energy system benefits, and reducing the carbon targets of the energy system from net negative to just 0 to reflect potential solutions development in currently hard to decarbonize sectors. The report also focuses on identifying the key actions required between now and 2050 to achieve the scale of deployment of each source of flexibility indicated by the model in the high flexibility scenarios. Now, this analysis has been carried out by first developing an indicative 2030 deployment trajectory for each source of flexibility using a simplified diffusion curve. These interim deployment goals have then been used to assess any barriers using the deployment readiness assessment framework shown on the right of the chart. And this framework considers market enablers, business models, and other key factors required to successfully deploy flexibility on a large scale and assess whether each factor is helping or hindering Great Britain's progress towards flexibility deployment. The technologies assessed include demand-side response from small appliances, non-domestic demand-side response, electric vehicle flexibility, including both smart charging and vehicle-to-grid, thermal energy storage integrated with district heating schemes within buildings, electricity storage, and hydrogen electrolyzers. And so on to the key findings, and we have three sets of these. And the first of these focuses on that core question around the role and value of flexibility. So firstly, as we've heard already today, investing in flexibility is a no regrets decision, as it delivers material net savings of up to 16.7 billion per year across all net zero scenarios analysed in 2050. Across all the heating scenarios, flexibility always delivers a net saving ranging from between 9.6 up to that 16.7 billion in 2050, and supports cost-effective decarbonisation of the energy system. The savings predominantly come from the avoidance of gas generation, reduced reliance on carbon negative technologies, and reduced network reinforcement. The second key message is that developing a portfolio of flexibility, including on the demand side across the energy system, is an effective strategy to manage uncertainties and reduce costs. Delivering flexibility from multiple sources across the energy system reduces the system cost impact of price shocks or technology unavailability. We find a variety of flexibility sources being deployed across all heating scenarios to minimize system costs rather than a few dominant ones given their individual value. However, whilst a portfolio of flexibility technologies can adjust to changes in the relative availability, the system cost impact is greater if a type of flexibility is removed completely. For example, if sources of demand-side response across domestic, non-domestic, and electric vehicles are not developed and available, this creates significant pressure on other sources, leading to an overall increase in system cost of up to £4.5 billion per year in the electric heating scenario. So it really underlines the importance of those demand-side flexibility sources and measures. The third point is that exactly that point, the embedding flexibility in zero carbon heating and transport solutions will help to reduce their system impact and costs, making their decarbonisation economically more feasible. Now, having smart charging and vehicle to grid allows large-scale EV charging to be delivered aligned to renewable generation, whilst reducing the impact on the network through peak demand reduction. Similarly, having large-scale deployment of thermal storage allows the heat demand to be made flexible. And there's an additional benefit through the coordinated interaction between energy for heating and EV charging, which helps to reduce further overall system costs, highlighting the importance of coordination between different flexibility sources. The fourth point, which again I think we've heard already this morning, is that flexibility supports the net zero system cope with the dark, cold, windless days in winter. It's important to consider the impact of weather patterns that cause very cold temperatures and very low wind speeds in a system that has a high penetration of renewables. Study has considered such an event across all scenarios where there's a 72-hour period of extreme cold weather, driving up heat demand, but coinciding with very low wind and solar PV output. The addition of flexibility helps to reduce peak demand for electricity and heat during this high stress period, which helps to significantly reduce fossil fuel generation capacity required and its associated costs. Now, for example, the deployment of additional flexibility in a fully electric scenario displaces over 90 gigawatts of unabated gas generation, which predominantly supports the system during peak stress times. And the fifth point here on this first slide is that we found that flexibility is deployed more locally in 2050, but delivers significant value at a national level. So of course, a large proportion of flexibility, as we've heard, will be distributed and be deployed locally, closer to demand. Analysing the benefits of deploying flexibility across different regions in this study suggests significant value is returned back to those regions via savings in local distribution network infrastructure. Now, whilst these are material, we did a study looking at London as an example, saving just under £500 million per year. The local flexibility also unlocks close to twice the amount for the wider system, almost £1 billion per year. So this really highlights the significant system-wide value of flexibility that's installed locally. Then the next slide, we see taking a broader look at the wider system considerations in reaching net zero in 2050 and the role that flexibility continues to play. And I'm sure as you will appreciate, the first point here is clear, is that reaching net zero in 2050 whilst meeting security of supply requires an unprecedented build out across the energy system. Regardless of the scenario and sensitivity, the 2050 net energy system is significantly larger relative to the current Great Britain system, particularly when additional flexibility is not deployed. Now, across the core heating scenarios analysed, the total electricity required to be delivered in 2050 rises to a maximum of over 800 terawatt hours, which represents a threefold increase relative to 2019. The network build-out required is also significant, driven by an increase in total peak demand on the distribution network of up to 228 gigawatts in an electric heating scenario. Flexibility present in the distribution network needs sufficient capacity to be able to charge up and discharge in response to system needs. Therefore, investment in networks is also important to unlock flexibility that can deliver system benefits. The second point is that pushing the energy system to go beyond net zero carbon has material cost and infrastructure implications. The cost of meeting a net negative carbon target of minus 50 million tonnes CO2 by 2050, compared with a zero target in 2050, could add up to circa £5 billion per year to the energy system. The increase in cost in our analysis is primarily driven by additional electricity generation capacity and negative carbon technology deployment in the hydrogen heating scenario where this was analysed. Now, beyond just the scale up of the energy system to meet negative emissions, this target has an implication on the wider system, including the cost optimal strategy for heat decarbonisation. For example, a more stringent carbon target in a hydrogen dominant scenario reduces the proportion of hydrogen generated via natural gas reformation. And there's much more detail in the report on those sensitivities. Explore that. The third point is that carbon negative technologies have an important role to play to help meet that net zero target in 2050. There's a consistent deployment of negative emission technologies, including biomass energy, CCS, and direct air capture and carbon storage across all scenarios analysed. A key finding from this study is that negative emission technologies are important even when the carbon target for the energy system in 2050 is zero rather than net negative. And this is driven by the need to negate emissions from the use of natural gas for electricity generation, hydrogen production, and/or for home heating via hybrid heat pumps. While the deployment of BECCS is linked to the level of hydrogen demand in the system across heating and other uses, direct air capture is predominantly linked to the use of natural gas in the system. In scenarios of significant natural gas use, such as the hybrid heating scenario, unavailability of DACs drives heating to be predominantly electric, needing significant additional build-out of renewables and CCS capacity. The flexibility minimises the cost increase due to peak demand management and capacity optimization. Our fourth point here is that any dominant single heating solution has a significant cost and infrastructure impact on the energy system. Great Britain's choice of heating decarbonisation has a significant impact on several aspects of the energy system, including scaling up existing technologies and networks to needing new technologies, including those that can negate carbon emissions. For example, a fully electric heating scenario without additional flexibility requires significant additional electricity generation capacity, some over 400 gigawatt hours required, with the current capacity sitting just over 100 gigawatts. Similarly, a hydrogen heating scenario needs a significant scale up of relatively few technologies, such as electrolyzers, hydrogen storage, bioenergy gasification plants, including CCS infrastructure. And our last point here is the use of hydrogen across the energy system, which brings carbon and cost benefits, as we found, but requires a portfolio of production methods and the availability of CCS infrastructure to make it happen. The ability of the system to optimize hydrogen production to high energy supply times, store hydrogen, and then use it for heating, power production, and other applications across transport and industry drives this value. This optimization enables significant cost reduction in network and generation investment relative to an electric heating scenario, in which this level of system-wide coordination is simply not possible. Integrating additional flexibility into a hydrogen-dominant system has a significant effect on cost reduction and has the largest impact across all scenarios in terms of reducing the total electricity generation capacity requirement. The total cost, of course, of the hydrogen system is sensitive to technology costs, fuel costs, and availability of carbon negative technologies. Therefore, retaining a diverse portfolio of hydrogen production routes, gasification, reforming, and electrolysis, along with the integration of flexibility, can help to avoid shocks if one or several of these dependencies becomes expensive and/or unavailable. However, even across this diverse portfolio, the ability to deliver hydrogen needs across the system cost effectively is dependent upon the availability of CCS infrastructure, without which significant additional costs will be incurred. So moving on now to the considerations to deliver this flexibility and the smart system. First key point, of course, is that consumer engagement on flexibility beyond commercial value is critical as a critical aspect to scaling up flexibility technology deployment. Unlike previous decarbonisation challenges such as large-scale generation, the rollout of flexibility needs to be considered across all stages of deployment. Now, taking a rational approach to consumer engagement that is focused solely on commercial value is unlikely to put the sector on a pathway to achieving the gigawatt scale required to deliver material system benefits. Understanding consumer needs, crafting appropriate narratives for different segments, and building them into user experience requires significantly greater focus in technology development and demonstration programs going forward. This is especially critical for the success of DSR, demand-side response, electric vehicles, and thermal storage flexibility, in which the flexibility integration is tied to the broader challenge of consumer acceptance of new solutions for mobility and heating. Second point I'd like to make is the report found that flexibility should really be integrated into enabling infrastructure, including low carbon heat and transport solutions from the start. Now, a key consideration across the different flexibility technologies assessed is the importance of enabling infrastructure for its cost-effective and large-scale deployment by 2050. For technologies such as demand-side response, both domestic and non-domestic, this is about ensuring smart meter rollout does not face additional delays and having a clear route to secure, cost-effective data access across millions of potential sites and devices. For technologies that are tied to broader strategies around heat and transport decarbonisation, it's important to build flexibility into technologies and service offerings right from the start, rather than retrofit in the future, which could make it prohibitive. Examples of such integration include thermal storage and district heating schemes with heat pumps, and building in smart charging across all electric vehicle charging points. Okay, to make all this happen, of course, the third point is around that creating that evolving kind of regulatory environment, which combined with low financial gains in the long term, does create challenges around business model development. The business models for flexibility have to straddle the constant evolving regulatory environment that affects how to access and what the value of flexibility is with the consumer need for consistent and secure revenue streams. Improving routes for cost-effective data access, leveraging the significant investments into infrastructure, such as the Data Communications Company, will alleviate some of the cost burden in the business models and avoid redundant investments. Fundamentally, market signals need to reflect whole system benefits across generation, networks, carbon savings, and system security to incentivize the effective deployment and operation of different flexible technologies, including those on the demand side. This will be required to effectively coordinate between actors to support deployment of flexibility for not only their benefit, but also for the wider system. Greater focus to ensure market signals incentivize consideration of flexibility into infrastructure, even though that system value in the short term might not be present or material, will be important and critical. Fourth point is that a smart and flexible system can only be enabled by digitalization of the energy system. The value of flexibility is unlocked through real-time coordination between assets to operate in sync to deliver whole system benefit. For example, we see the coordination between smart electric charging, EV charging, vehicle to grid, and thermal storage in heat networks working together to minimize demand during periods of system stress. These assets sit at different levels in the energy system and across different vectors and between different ownership boundaries. Therefore, a critical consideration to enable this future is the need for digitalization across the energy system to allow information sharing, monitoring, and coordination between assets and organizations at this scale. And the last point here is around innovation and making the point that continued efforts for new technology development and innovation focused on cross-vector integration is important to have them ready in time. The study has found significant flexibility deployment needs by 2030. Innovation is important to bring technologies such as thermal energy storage and electrolyzers to the market at the appropriate cost point and technical capability ahead of 2030. And given the linkages between these technologies in the wider system, particularly electrolyzers, it is important to design and integrate them from a whole system perspective rather than in isolation. For technologies such as demand-side response, battery and thermal storage, and electric vehicle flexibility, deployment efforts should focus on cost-effective system integration and engaging consumer experience going forward. Additionally, a greater focus on innovation that demonstrates cross-vector flexibility is important to understand the issues and scale of complexity, both at a technical level, a regulatory level, and at a social level in delivering this in practice. So those were the key findings. There's, as we've heard before, there's much more, of course, in the report, and they're very broad and go and touch on a number of different areas across the energy system. On my final slide here, again, just to reiterate, there are a series of sessions over the next few days to cover different aspects of the energy system and how flexibility plays into those. After today, tomorrow on Wednesday, we'll take a closer look at the Net Zero Challenge with the impact of energy system carbon targets, looking at the interplay between CCS and flexibility. And we'll also get closer to those smart technologies and how do we value those, how do we value flexibility, how do we value and enable some of those 2030 indications and targets. How do we prepare for new business models and new opportunities? We have Chris Stark from the Climate Change Committee opening tomorrow's session with the keynote. On Thursday, we again explore from a different perspective the important role that flexibility has on major energy system infrastructure decisions across electricity, gas, and hydrogen. How can infrastructure developers and operators best leverage and support through effective coordination to unlock whole system benefits? We'll also explore what's to be gained from taking a whole system deployment of flexibility. And we'll hear from a few experts on some case studies of what is already happening in Great Britain to deliver a flexible system. So we have a good range of external speakers and a series of panel discussions to debate these questions. And I encourage you to engage and join the discussion and the debate through the week. Thank you very much. I'll hand back to Janet.
Well, thanks very much, Andy. It's really interesting stuff. Now let's hear from Goran Strabak. He's the Professor of Energy Systems at Imperial College and has led development of novel advanced analysis approaches and methodologies that have been extensively used to inform industry, governments and regulatory bodies about the role and value of emerging new technologies. He's going to talk about modelling for the new report and the importance of taking a whole systems approach. Over to you, Goran.
Thanks, Janet. If you could, my slides, much appreciated. Imperial team has been grateful to be involved in this activity to provide some fundamental modeling evidence which should provide information as to how we should move forward to facilitate cost-effective transition to low-carbon system. And I'll in here focus on the whole system approach, but also mention a little bit about our modeling side and then illustrate some of the core results which demonstrates how relevant the flexibility is in the whole systems approach. So the next slide is just an overview of the presentation, which will, as I said, the focus will be on the whole systems approach and what's the difference between silo versus if you consider energy vectors separately. A little bit about our model and the key findings. Just to see again, showing that the flexibility has got a major role to play, and this will be a really in terms of there are massive uncertainties, but this is a no regret decision to move forward into this digitalized smart world and integrated system. And also this is this also includes the analysis of the transport and heat and how this is going to reduce the old system costs, and also and we mentioned there is also significant interaction between local and national level objectives, and that's something which is also we think is also a kind of novel and important aspect of this modeling, and also this cross-vector integration, as we mentioned. And also we also need to make sure that we can deal with these extreme events which are taken into account in this modeling. So the next slide shows just a kind of a high-level picture. You can't see all the details, but this is all the vectors are presented in this slide, showing that we've got interaction between them, between power, gas, hydrogen, transport, CO2 networks, and so forth, and we need to look at them comprehensively and from the whole system perspective, rather than in isolation. And this is one of the important aspects which is coming out in here. In here, obviously, we've got any kind of the supply side, different technologies which produce energy. On the right-hand side is demand. But of course, in between are various technologies, but also different transport sectors. And for example, this modeling includes electricity networks, gas networks, hydrogen networks, CO2 networks, and heat networks. And these needs to be considered in a coordinated way in order to get this cost-effective decarbonization approach. And also, we have analyzed, as I mentioned already, these severe weather events, and also there is also given significant uncertainties. Although we won't discuss this in detail today, in terms of also from the whole system perspective, this modeling can provide information about what is the role and value of different technologies, which can then provide information about how relevant that would be to incorporate and to understand where the work and innovation is required to make this cost effective. The next slide demonstrates just again showing this interaction between the spatial and temporal resolution. So we've got a kind of at a high level from the street level infrastructure, which is on the left hand side, because that's where the significant amount of flexibility resources will be towards the end use. And we also need to analyze at the national level how that works, but also in this modeling we've also included interaction with Europe, because the interconnection is also has got also significant role to play in facilitating the overall European system decarbonization. Also, then on the time scales, kind of we are moving in here from fraction of a second to multiple years. And this is also critically important because the balancing of the system now with increased amount of variable renewables, and potentially also the inflexible nuclear to make demand supply balance in real time, and given also the significant reduction in system inertia from renewables, is critically important to have these auxiliary services regarding the frequency regulation and various forms and reserves needs to be included. So the time granularity is also one of the core aspects of this modeling. You have seen the next slide is Andrew's already shown this, so I won't spend too much time on this, just to show that again that we've got these on the left hand side top, we've got these three heat pathways. And then we got the flexibility, the next one showing that you can see batteries, pumped hydro, thermal storage, and so forth. I just wanted to mention here that that in this use of these particular demand side resources for flexibility, just to say that fundamental assumptions in here is being made that we would use this flexibility, but without compromising service quality delivered to end users. So there would be what the users, what the consumers want to have will be always delivered in time. Just that we use flexibility resources, but not compromising the service quality delivered to end use. That's also an important aspect of that. And obviously, there can be sensitivities in there, but that's an important aspect. The next slide demonstrates these three core decarbonization pathways, you can see at the bottom it says hydrogen, electric, and hybrid system. And there are 2 bars in each of those. One is low flex, and the other one is high flex. And at the high level, you can see there is a very significant reduction in costs. It says in here 16.7 billion pounds a year if we have the flexibility, which is obviously critically important. But also it is just to highlight in here as well that in this analysis, given the assumptions, which again potentially can change situation, is that the hybrid system with using hybrid heat pumps, which means continuing using gas in the negative emission system, is turned out to be most cost-effective concept. Then the next one is hydrogen, which is on the left-hand side, and the kind of the most costly was pure electrification. And again, as we probably discussed that later, there are obviously significant assumptions in there which potentially could change it. But again, the flexibility is the core. And just also to mention that we were a bit surprised when we found out that the hybrid system was there, because we are talking into the negative emission system, and it turned out that continuing using this, given the assumptions, continuing using gas for heating as a part of it is it turned out to be most cost effective. Although obviously gas has got emissions, but of course in here we'll see later on that the volume of gas used reduced significantly, more than 10 times. But the value of having gas to provide flexibility to reduce the investment in generation and networks had a major role to play. And obviously this bit of gas is also obviously being the CO2 is being taken on by the carbon capture and storage, so that there was a bit more investment in this in this infrastructure to capture the carbon. But on the other side, the benefits were very high on the system side. But the key in here is that we have in here analyzed kind of single solutions across the UK, each of these particular pathways, and of course something which is also we think would be important maybe going forward to see what potentially could be that all of these pathways could be in different regions, so that there may be potentially an important aspect of having that in the coordinated fashion. And also just also to mention that also this in the whole systems approach in here, the modeling inherently co-optimizes the operation and investment across the energy vectors, so that that's where the flexibility is critically important. And also in this hybrid and hydrogen system, there is inherent flexibility, and this is what reduces the costs. And the greatest savings, Zandi mentioned already, is the network and generation costs is where the key benefits are. If we just look at now the next one, showing where the flexibility actually is, and what is important to have in mind in here, that the flexibility historically comes from large-scale generation. This is how we balance demand and supply historically in real time. But in here we are now introducing, flexibility is now coming broadly from the end use. Obviously there is interconnection, and we'll show later on, the electrolyzers and so forth. But lots of it comes from the end use level. And so, for example, you can see in here with the hydrogen one, what is the volume of flexibility in power sector, and what is the flexibility in the heating sector. So you can see that, for example, in hydrogen scenario, there is this red one, which is in all pathways in the power, is to do with having the smart charging and vehicle to grid. Flexibility from transport sector is an important aspect. There is also interconnection is also seen to be potentially having a visible role to play. Now, on the heat side, you can see the yellow ones. This is to do with the district heating. Thermal energy storage is the kind of light yellow, and the other one is to do with the having the thermal energy storage in buildings. So thermal energy storage, you can see, has got a major role to play, and also given also it's a very cost effective, because, for example, district heating, what you need to have is the hot water tanks in the in the system, which is not that expensive, but you can see that we are talking about significant amounts, hundreds of gigawatts of that, but it generates very, very significant benefits at the national level, and also reducing the investment in networks and the generation system. Also, in the electric system, is also interesting to see that the very large flexibility is in there. In addition to electric vehicles, and in the connection, there is a black one, which is to do with the battery storage. You can see in here there is a kind of nearly 80 gigawatts or plus of battery storage being seen to be cost effective to facilitate, again, this cost effective transition to low carbon system. So you can see that in each of these areas that there is a very significant aspect on the power side, in particular from the end use demand, which is going to play a major role, and also the heat, because the heat decarbonization of heat and transport sector is where the big challenges are, and this is where the flexibility comes from. Next slide shows the importance of interaction, coordination between local and national level infrastructure, and this is showing at the left hand side, just showing where the significant reduction in cost is, and one is to do with the distribution networks, and also the whole system benefits. And we can see in here that the 15.8 billion pounds is the savings, that there is you can see in here there is a 0.48 is the local flexibility in terms of the local district, but there is also nearly 1 billion flexibility associated with supporting the national level. And this is something which is what we have also demonstrated here, that we need to coordinate and have a coherent approach between local, district, and national level infrastructure, because the coordination of those two together brings very significant benefits. And that's something which also on the policy side, is on the agenda, but still a long way to go. We hope that this activity will provide some fundamental evidence to which will provide some information and evidence as to how we should try to integrate. Because in here at a high level, what it demonstrates, if you invest more in the local infrastructure, for example heat, then you would make savings at the national level. And this is something which the policy framework, regulatory framework, to make that happen would be also very important going forward. The next slide is just showing the interaction between the gas and electricity infrastructure, which provides very significant savings. We've done just analysis in here to show the first bar on the left-hand side shows that if we ignore, if we kind of design the electricity system and gas system in isolated mode, and this is a hydrogen pathway, that there would be higher costs associated with this, and this is fundamentally to do. But if we integrate them, if we think together, then we've got savings of 5.6 billion pounds per year. And this is where this is showing that what actually happens in here is that you can see on the right hand side is the hydrogen demand and hydrogen production, what happened to be the case that the hydrogen demand, in fact, increased a bit. And what happened also, and also the electrolyzers were installed, because in the base case, if you look at the silo, given again the assumptions that the blue hydrogen was more cost effective than having electrolyzers and green hydrogen. But what then this modeling demonstrates, when you look at together, in fact, that it is in fact worthwhile having also green hydrogen production and use electrolyzers to make that, because that also, first of all, made a better use of significant contribution of offshore wind, which is also not easy to incorporate all of that. By having electrolyzers, you can make that work, and also electrolyzers can also help with the system balancing. That we can then reduce the amount of first of all, we can reduce the amount of operating costs. We are going to reduce significantly the gas which is being used in there, and that would also reduce the appropriate operating costs. When I was saying here that the cost kind of reduce nearly 3 times, although there is a bit more investment in the electricity generation, because we are going to build a bit more wind, but we're going to make better use of it. So this is just showing that again the interaction between the two is a very important aspect of this, and also that this also incorporates also the increase in also the hydrogen transport costs. All of that is included, but still overall is rather than using we can in fact make better use of renewables and use hydrogen to produce electricity in here, which is running the say CCGTs, which also can provide flexibility and energy rather than only gas. So this is just showing again that there is a significant benefit to think in a coordinated way through this through this process. Now the next slide is just showing the this is the same case, but when we have, for example, this is a 4 bars. The first bar is kind of the silo approach. The second one, when we got a kind of partial coupling, we produce hydrogen, but we don't actually use it for electricity production. Then the third one is when we use for electricity production, and the fourth one when we have the full flexibility in place. And that you can see that all of these aspects are showing visible benefits in this scenario. Also, we have the next one is showing the same situation, just that we've got now the electricity infrastructure, but showing again that having this coordinated approach by actually, although even if we've got an electrified heating sector, we still want to have interaction between hydrogen and electricity infrastructure. And this is just showing that we've got also visible savings. Again, this is again to do that we are able to reduce the system operating costs quite significantly, and also in the flexibility again we also reduce very significantly obviously the networks, because that's one of the big aspects of the electricity pathway is we would need to kind of dig the roads and put all new cables in. But if we've got flexibility, we can reduce those investment, and also we can reduce the investment in the generation assets while still meeting the target. So the next slide shows this use of CCS, which is one of the critically important technologies to deliver the negative emissions. Although, as you may know, there is a still significant, very big uncertainty as to how this would actually work, and still there is still quite a lot of concerns about feasibility of that technology and also the cost and so forth. So we have done in here just a sensitivity assessment to illustrate how relevant that is. And this is just to we've got in here again, the first two bars are low flex and the last two are high flex. But the first two, the first one is to do with the core. When we have a low flexibility, but we do have the hydrogen heating. But then the other one is, but we've got a blue hydrogen in the first one. But the second one is saying, imagine we do not have CCS, so it has to be green hydrogen. Then you can see that the costs increase quite visibly, nearly 20 billion pounds. That's again to show that the CCS, is potentially got a very significant role to play, and in order to find the balance between green and blue hydrogen. And this is just showing that in this context that is an important aspect. And then the other one, the high flexibility, just showing that that the increase in costs, if we go to high flexibility, would be lower because we can make use of the flexibility to reduce the need for this amount of energy, and we can make that more cost effectively. So the next slide is showing this comparison between electric heating versus hybrid heating. And you can see on the left-hand side, the bar showing where is the heat coming from, and that we have that in both of these cases, electricity. You can see that we've got we've got heat pumps. We've got the large-scale heat pumps, which are in district heating systems, ground source and water source heat pumps, which are used because there are some areas where the district heating is very cost effective. And then electricity scenario, you can see that all other heat is coming from electric heat pumps, while on the right hand side we see that some of these we also got a hybrid heat pumps, which means that we got also boilers, and natural gas boilers are also in there at the top of like so this is, I say, was very also informative, because you can see that the volume of gas used to provide heat is a kind of less than 10%, if I put it this way. But the value of gas, if you look at on the right hand side, in terms of the costs, is very, very significant. And that you can see where the big savings are fundamentally is to do with the top bars. You can see is the blue and light and blue and dark blue, showing the changes in the investment in generation assets, because during these extreme conditions, when you have a few days very cold, then if you want to maintain this, you would then need to do this, to use the electric heat pumps. Then they would need to be used, and that would require significant really all replacement of distribution assets and massive build of the generation to meet that peak. While if you got a gas in here, then we can use gas during those conditions and significantly reduce the need for reinforcement of distribution networks, electricity infrastructure, but also the reduce the investment in peaking plant. And this is again to show that, of course, there is a more investment than to in the CCS, but the overall balance was such that it was actually cost effective to use gas in this context. And just to briefly mention, the next one is showing this extreme days. So this is just a week, Monday, Tuesday, and so forth. And then this is the demand with the low and high flexibility. So you can see that with during these Wednesday, Thursday, Friday in the middle, there is a very significant increase in demand. And that's also to do with two aspects. One is the heat sector, demand is increasing because it's in here. These are extreme cold conditions, and that's again based on the analysis which is being adopted by government, that we need to be able to, because we currently gas can deal with supplying the heat during 1 in 20 years cold winters, and the question is if we do something else, how that would work. And this is just illustrating that if you've got the flexibility, also there is in here demand also comes from hydrogen production, electrolyzers. So all of that can be, and also using thermal heating in particular, that we can in fact nearly make these flat demand during those conditions when we got these very significant requirements for heat, and we can actually make that reduce that demand very significantly. But also we are also going to, in here is reducing also the electrolyzers, so that would then require very that would then lead to significantly reduced investment in the infrastructure, which is one of the core aspects of this. But this is also taken into account. And the next slide is just showing the report, which and there is also at the top is the link, and just highlighting what the structure is. We've got overall the current system and introduction of the forms of flexibility in the chapter 1. Then we've got the description of the IVIS model and all the scenarios which are being used in here, and then the 3 chapters are showing then the results of the modeling for this 2050 scenario. Then also there was also analysis which Carbon Trust carried out to see how we're going to move there and what would need to happen by 2030, given what the targets are for 2050. And then the chapter 5 is setting out the recommendations and the core findings of this modeling, so that we can try kind of set out what are the key findings. But also there is also significant amount of aspects which would potentially require further analysis to provide more detailed assessment how we could and should move forward. And I will stop at that. Thank you very much indeed, colleagues.
Well, thank you very much, Goran. And I'm struck actually listening to both of those presentations by how much, when we think about what the no regrets actions are that we can take, they're not so much actions as a way of thinking. Digitalize the system, put in flexibility at every level, and really think wider than just the electricity silo or the heat silo or the mobility silo. Very interesting change in the way that we're thinking, or evolution in the way that we think. Well, I'm very glad to say we've got an opportunity now to have a bit more conversation about what's happening in the report and the results. I would just remind you that we have got more sessions talking about specific aspects of the report over the next couple of days. And I'll also remind you that you can submit your own questions, which we may pick up on now or move into one of those dedicated sessions. If you look on the right-hand side of the screen, just a reminder, you'll see various tabs, and to send in a question, you should click on the Q&A tab and press the blue plus button. Your questions will be anonymous, and you can upvote questions, so we'll know where the feeling of the meeting is. So I hope that I have got Andrew and Goran ready to take a few questions from me. I can't see them on my screen. Well, perhaps if I just pitch in with the first question, I hope that the managers will bring up the answers. There we go. I thought I was going to have to answer the questions and answer them myself as well, which isn't the way we want to go. Okay, I'll just dive straight in. So you've described this report as groundbreaking, but there is a lot of work happening on whole systems in a lot of different organisations at the moment. How can you justify that description of it as groundbreaking? who'd like to go first?
Oh, sorry.
Goran, you're on mute.
Sorry. There is definitely a significant amount of work going on in the modeling side, and we are moving forward, in different areas. But where one of the core strengths of this particular modeling is this granularity across space and time. We are looking from seconds to years, and this is one of the, and that's critically important because the management of demand-supply balance in real time with increasing amount of renewables is very, very big challenge. And we demonstrate, for example, that by 2030, just to give an example, that the energy production costs, electricity production costs would reduce for 50% because we are going to have renewables in there with a zero marginal cost, but the ancillary services costs will increase more than 15 times. And this is all to do with this balancing of demand supply in real time. And the second aspect, which we think is also important, which is kind of our element, is also to be able to look at this local versus national level modeling. And we have been working a lot to integrate, which is being very, very complex, and we have published some papers in this area as well. How you look at how do you look at local infrastructure, and where is the balance? How would you manage that? For example, if wind is blowing hard, you want to increase demand to capture wind, but if you increase demand, you will overload the local networks. And where is the balance? And this is also critically important to put that in. That's something which is kind of a feature of one of the unique features of our modeling, and also this link with European system is also what we think is also relevant to have, because this more of a holistic approach also brings visible benefits, and that's also something which is also one of the important aspects of our modeling.
Maybe
did you want to add anything?
Yeah, no, thank you, Janet. Yeah, thank you, Goran. I think you covered that quite comprehensively. So, I mean, I think maybe a broader aspect, maybe moving away to the specifics of the modeling, but the very nature of the work over the last 18 months has been to work with that cross-sector, kind of cross-vector stakeholder group as well, and partnership group. So we were very keen to ensure this wasn't just, for example, just an electricity kind of group, but it was truly representing, what are key sectors across the industry, and even to extend that to the other stakeholder group, as I mentioned at the start, with BEIS and Ofgem, climate change. All of these kind of key stakeholders very keen to keep close and engaged over this period to make sure that the report and the analysis and the assumptions were all transparent and robust and as relevant as possible to kind of make sure that this is a robust and useful evidence base for the sector.
Okay. Let's talk a little bit about some of the assumptions that you've made behind the modelling. For example, you've assumed that the level of nuclear will remain constant, although we are facing closure of quite a lot of the existing fleet, all of them on that long period. So can you justify that? And you've also limited the amount of interconnection. Is that because you think the business case falls away at that level, or is that for purely for modelling reasons?
Yeah, thanks, Janet. Maybe a general comment on kind of the assumptions before maybe I'll let Goran pick up those specific questions on nuclear and interconnection. But again, all assumptions were kind of discussed with the consulting partners. Publicly available sources were used, so there's nothing kind of opaque in there. And indeed, all of those will be published in a separate document, which will be available on the website as well. So people can unpick and see what we're assuming and the where the data has come from. And I guess more broadly, of course, that there's a lot of scenarios in there. There's a lot of sensitivities in there. So we're very keen to pull and push the energy system to really understand, those interactions with nuclear, with CCS, and how flexibility plays into that. So maybe just a general kind of comment on just our approach to the modelling and the report. But yeah, I'll let Goran come in on those specifics.
Yeah, but just to say, I mean, regarding the assumptions, this is just kind of agreed assumptions, in these discussions. But of course, there are some case studies showing that, for example, nuclear increases massively in some of the scenarios, particularly if we move to this fully on the green hydrogen and so forth. So there is it's all to do with assumptions. But again, the sensitivity studies should be carried out to see where is the what are the changes and how the balance is done. But this was just an assumption. But there is also kind of assumption, much more nuclear, but also no nuclear, if you like. If we do production from energy from renewables and produce hydrogen and run hydrogen-based generation, that's also scenario. This is just it all depends on the assumptions made, but this is just a kind of a core case study which was done. The same was applied with interconnection in terms of these two scenarios with interconnection. Although there is and we also said that we could do further analysis to analyze the interconnection, because there is, for example, now very, very big debate in Europe regarding the offshore wind deployment, and there is a more than 490 gigawatts now is the projection, and there is a much more offshore wind in the UK waters than what we would want to use inside UK. So there will be also interconnection potentially to support that, but that is a kind of not wasn't a focus of the study, but definitely it's an important question that that interconnection across North Sea, across Europe, would potentially play a major role in supporting that cost-effective transition.
So that could be bigger than the level that you've used in the report at the moment.
Definitely, yes.
Yeah.
Yes.
You've also given quite a substantial role in some cases to negative carbon technologies like direct air capture and biomass with carbon capture and storage. The first one is certainly unproven, and the second one is quite contentious over the fuel use. What happens if those technologies are not available at this kind of scale that you've looked at?
Well, here the first to say is that these negative emissions assumptions in the modeling is to meet these zero carbon target, and this is what this is what drives the need for direct air carbon capture and storage and bioenergy carbon capture and storage. We just need to have them in there in order to make completely agree that there is a lot of uncertainties around those technologies. But this is what the assumptions were, and we have also done analysis, looking into, for example, if ducts are not there and so forth. So these sensitivities are carried out, but this is just to say that given the assumptions to meet the negative carbon target, because it is difficult to decarbonize some other sectors, aviation, agriculture, and so forth. This is just based on assumption. We completely agree that there are very significant uncertainties associated with costs and availability of these technologies, how they're going to work. But this is. But we've also done assessment, also analysis if there is no ducts and BECCS, and I show that you would just need to have a significantly more blue hydrogen being used, of course, and much more wind and so forth. But this is just we've done sensitivity assessments. We completely agree that there are big uncertainties associated with the availability and cost of these technologies.
Andrew, did you want to add anything?
Yeah, no, I think Goran has kind of covered things there. I mean, I think getting to net negative emissions is a challenge, and there's no kind of silver bullet technology out there currently that achieves that. So I mean, I think what we've shown is that these technologies, if they're available technically, then they're deployed, from a cost-effective perspective, and that the whole modelling report was done on that cost minimisation basis to get to that net negative scenario. So really, the challenge is there for all of us to do better, and that's almost the gambits down to what else can we do, because the alternatives, if we don't have them, are potentially much more expensive energy system. I think that's what the report says as well.
That's an important thing to go at there then. Well, we're certainly seeing some questions coming up about the role of hydrogen and how we make decisions there. You've looked at the extremes in the types of role it plays, and I think that's deliberate to get a range of futures and see the kind of decisions that the model makes. What does it tell us about real-world decisions in deploying hydrogen?
So yeah, maybe I can start, Janet. So I think hydrogen across all the scenarios had a role to play, and again, from a technical and cost optimization perspective, it was used and it was utilized and produced, and I think as you said, the kind of wider energy system decisions you can't be taken in isolation to those decarbonizing heat scenario strategies. So I think we do need to, when we're talking about heat decarbonization, look beyond just the specific sector and demand and look at what that means for renewables and potentially with electrolysis. Our modelling, of course, showed, and Goran's modelling showed, that CCS, from a cost-effective perspective, from steam methane reformation, is deployed and used. And so we conclude, that it's not one or either of green and blue hydrogen, but we actually need both to play their particular role within the energy system. So I think, again, the electrolysis is great coupled with offshore wind, for example, to use that excess generation, avoiding curtailment, storing hydrogen, and then pushing it into the system. CCS, I guess under our assumptions is maybe a little ahead on the cost perspective. So all of these considerations go into the kind of system dynamics, and what of course happens is that we need a bit of both. So I think in terms of real world decisions, it's absolutely continue to innovate and continue to push on technology proving and cost reduction on both, if we're calling them green and blue hydrogen technologies. But yeah, Goran, I don't know if you wanted to add any.
Well, just very briefly, just to mention that the hydrogen was present in all scenarios, and this is all to do with the fact that, given the assumptions again that there is industrial sector which would switch to hydrogen, and so the hydrogen was visible not only hydrogen heating but also in the other sectors. So and what Andy mentioned is that it was demonstrated from the given the assumption from the system perspective that there was a role for both blue and green hydrogen to play. And as we mentioned, green was coming because of this interaction, which was reducing the costs. But both of those are they've got a role to play, given where we want to go.
Perhaps I should just remind people that we usually use a shorthand of green hydrogen as that produced by electrolysis, which obviously we hope eventually would be the power would all come from renewables. And when it comes to the blue hydrogen, is our shorthand for hydrogen that's produced from gas using steam reforming, but the carbon emissions are captured using carbon capture and storage. And I think between those two different types of hydrogen production and the requirements of the electricity system, you found some unexpected interactions between the renewable use and hydrogen production. Would you like to draw out some of the interesting points that we discovered about how those three systems interact or conflict with each other?
Yeah, I mean, there was regarding the green hydrogen, as I say, the fundamental, given the assumptions which we've taken, is that blue hydrogen, if you just look at what production of hydrogen, you would do blue. But when you look at the whole system, then it turns out that we want to produce a bit more hydrogen, but also there is interaction between wind and electrolyzers actually can make better use of wind. So if wind is blowing too hard and demand is not big enough, then you can produce hydrogen. So that was also one of the aspects which was which came out from the modeling, and also the electrolyzers, also which we made those assumptions, which is a kind of what the thinking is, can also provide very significant contribution to, this is a bit technical, frequency regulation and balancing services, because if you lose a big plant, you can switch off electrolyzer immediately, and therefore you're going to balance demand, so you can provide frequency regulation from it, which was also one aspect which, when you look at the whole system perspective, was also a benefit of green hydrogen. But there is quite a big kind of, to be a bit, different views in terms of hydrogen. There are some, in some areas is thinking about only blue, some areas being only green. Depends on what assumptions you make. And there is quite a uncertainty in there. But given the core assumptions and pathways in here, as Andy said, we got that that we've got a coordinated way. Both of those, blue and green, are in fact part of the in these in decarbonization scenarios.
Yeah, and absolutely, Goran. Maybe just to add, Janet. So the modelling, maybe some people were able to pick them from the charts that Goran shared. I think we capped offshore wind capacity to 120 gigawatts in 2050, which is basically 40 gigawatts per decade build out over the next 3 decades to 2050. Goran also touched on the kind of sensitivity to look at, okay, then, well, what if blue hydrogen with CCS, generated through natural gas steam reformation, isn't available, or for whatever reason it's not chosen as a policy choice, then that put tremendous demand for electrolysis as the kind of core hydrogen producing technology. And what that did was it pushed that 120 gigawatt offshore wind requirement up to over 220 gigawatts of offshore requirement. Now, whilst Goran's right in saying, longer term North Sea, there could be 300-400 gigawatts, to get to 200 gigawatts of build out by 2050 means building circa kind of 80 gigawatts per decade over the next 3 decades. So I think, and albeit, okay, that was within a kind of hydrogen heating scenario, but it does just illustrate the scale of investment that's required, but just how these trade-offs work. And again, coming back to the cost perspective, that was always the kind of the goal to achieve that, which is why that mix of technologies has value.
I'll just follow on from what Goran was saying by reminding our attendees that some of those ancillary services at the moment are provided by traditional fossil fuel plants, and finding other ways to maintain frequency and do those ancillary activities is an area of a lot of research at the moment. And I think there's a lot of interest coming from our questioners in this interaction between what happens locally and what happens nationally. Lots of the value in the flexible system sits in local networks, delivering flexibility locally. Locations have very different energy resources. I think Goran's already mentioned that as regards to different types of hydrogen that might be appropriate for different areas. Does the modelling provide input into local area energy planning? And our questioners are asking how national and local decision makers can work together to develop specific plans.
Yeah, great question, Janet. I mean, of course, the modelling does have huge input into local area planning, and I think it's one of the key findings is that flexibility deployed locally and has twice as much value to the national system as it does to the local distribution network. And really that's another great example of this kind of whole systems thinking, where you have to kind of stretch what the bound is of the revenue streams and the value that flexibility kind of unlocks. And that's a bit different to the way in which the system has been kind of operating, I guess, thus far. So what effectively we're saying is we need to kind of invest locally to get the benefits nationally, which is an interesting concept. And then that raises the question around, okay, well, how do the revenue streams flow from that? How do we, make sure that that value is recognised back within those that are providing it? And I think also this kind of cross-vector aspect around, I think we mentioned the thermal storage as well as vehicle to grid, help each other, and there's that optimization goes on at a very local level as well. So I think there's probably a number of things that we need to start thinking about, and it's that distribution networks or gas networks, engaging perhaps even more with the system operator to understand where those linkages are between those value streams that are national. I think from a kind of local area planning perspective, we would certainly advocate that kind of wider stakeholder approach where it's you are pulling together the network companies, the energy providers, the consumers, the demand points to really kind of create this cohesive kind of view around ensuring that we have a good view of the assets, we can, what flexibility is available there, and indeed investing. We did say that network operators need to invest to open up that flexible capacity to the national system. So there's a few different things at play there, and a few different interactions and relationships, I think, and discussions to be had. But yeah, absolutely, a lot of value there to be had. Goran, sorry, did you want to?
No, that's not that you cover this, but what you just said, for example, we also demonstrated that in some areas, in fact, it may be cost effective to reinforce distribution networks in order to provide more flexibility to the national level. So that's also, and so kind of these balances are critically important to have in mind, so that we can get a kind of optimal transition from the UK PLC perspective, but we need to have that, and this is on the positive side. This whole system concept is now on the agenda with Ofgem, for example, which we think is very, very important. So, but to be negative, that hasn't been resolved anywhere in the world yet. But there is a strong activity now, in the UK in this area. So yeah, I think it's we are in the right direction.
Well, perhaps we're running a little bit short of time, so perhaps I can wrap two questions into one for you both to wrap up. And that is you've obviously did earlier work on this in 2017, I think it was. So what have we learned from in the last 3 years, going from that work to this much more comprehensive work? And secondly, what's the next step for the work? Where do we need to go from here?
Maybe I can start that the 2017 work was focused on flexibility, which is also provided very, very strong evidence, but it was fundamentally focused on the electricity. It wasn't considering the multiple energy vectors, and this is something which this analysis is providing fundamental evidence, and also, as mentioned already, kind of this. Local national dynamics are also critically important for going forward. So these are the kind of the two, from the modeling perspective, differences, and this analysis demonstrates that the cross-vector coordination is going to play a major role in supporting this. So the flexibility can come from the proper coordination of the operation between different energy sectors. And this provides flexibility, which wasn't analyzed in the past, but that is something which is in here now very clear. Yeah,
absolutely, Goran. And maybe just to kind of build on that, but also pick up your last point, Janet, on your next steps. So I think because we have taken this kind of multi-vector approach, and we have identified where flexibility kind of plays some key roles within how we decarbonize heat and transport, etc., is that it really should be made that kind of core infrastructure challenge. So linking heat policies and transport decarbonisation policies with flexibility rather than kind of treating it as an add-on, I think is really important. The market design and the signals need to kind of start, continue to reflect those measures to meet the kind of net zero target. And that's important to allow the kind of flexibility to kind of push and recognise that value. And the business models, of course, that go with that, and the incentives to award kind of system value, I think, are some of the key things that we that we would say are the kind of immediate next steps to taking this forward and progressing it.
Well, we've had a question through about how electric vehicle batteries can help in increasing flexibility in energy systems, and I personally was quite surprised, in fact, by the slide that Goran showed, which had quite a significant potential from electric vehicle batteries, but also hugely bigger potential from what's in the heat networks and the potential for flexibility from there. But I think these are going to be questions that we'll dig into a little bit more over the next couple of days, because unfortunately that's all we've got time for today in this particular session. But it's obviously just the beginning of the Energy Transition Week. Over the next couple of days, we've got some deep dives into key transition themes and more on the outcomes of the flexibility report. Just to remind you, on Thursday, we'll be looking at infrastructure and a whole system approaches. So please mark that in your diaries. And tomorrow, we'll be looking at the Net Zero Challenge in the morning. And in the afternoon, we'll be looking at the role of smart technology. And I've certainly seen a couple of questions come up about how we manage that in this era of being very careful about cybersecurity and the protection of people's privacies. So some very important issues to dig into in both of those sessions. And I'm pleased to say the day will be kicked off by Chris Stark, Chief Executive of the Climate Change Committee. So that's going to be at 10 o'clock tomorrow, and I really look forward to seeing you all there. And meanwhile, we're encouraging you to use the time between now and tomorrow to explore all the content on demand, take a look at the report. It's all available on the main homepage under the Resources tab. You'll find all the information about the report and the report itself there, and other energy transition resources, including reports, briefings, and recorded webinars. But following that, I'll just have to wrap up the day. Thank you to Goran and Andrew for all of that information about the report, and I look forward to catching up with you and talking about it a little bit more tomorrow morning.
Yeah. Thank you very much. And colleagues, if there are any questions, please let us know. We'll be keen to look at the questions which you may have.
Thank you.
Thanks very much, and enjoy reading the report.